Hello friends, welcome back to our channel. In this video, we are going to discuss about subnetting and classless interdomain routing, which is also called CIDR. As part of this video, we are going to discuss about what are subnets and what are the uses of subnets. Then we will discuss about subnet mask and network prefix. So based on this subnet mask and network prefix, we would see how different classes of IP addressing would be obtained by discussing about classful IP addressing. After that, we would discuss about CIDR, which is classless interdomain routing. And then we would discuss about subnetting, which means how to divide a network into multiple subnets. Finally, we would go through different examples about CIDR and subnetting. So let's start. Let's start with what is a subnet and what are the uses of subnet. Subnet is nothing but a network inside another network. For example, we have a bigger network. So if we have like multiple devices attached to this network, we can segregate this network into different smaller networks, and each smaller network is called a subnet. So we'll have like multiple subnets which are formed from a bigger network. So let's discuss about the uses of this subnetting. First of all, it improves the network performance. So for example, if you have a bigger network like this, we have lot of devices connected to the network. As we discussed in the OSI model, these devices talk with each other by using the MAC addresses corresponding to data link layer of OSI model. So that means if D1 wants to talk with D2 here, D1 has to know the MAC address of D2. So for that, this D1 will send a broadcast packet to entire network. That means each of the other devices will receive the packet which is sent by D1, so that the matching address here D2 will send a response with corresponding MAC address. So if each device sends packets like this, there would be a lot of traffic within this network, which increases the congestion. And also, since every device will receive the packets sent by the source, then every device will be busy, and also the packets will reach every other device within the network. So the packets need to travel longer within the network. So if we divide this network into smaller subnets, for example, multiple subnets like this, then we'll have like lesser number of devices connected to each of the subnetwork. In this case, we are reducing the broadcast domain of entire network. That means each device will send the packets to minimal number of devices, so that we can reduce the congestion within the network, and also we can keep only few devices busy in receiving the packets, and also the packets will need to travel lesser distance within the network. So this way we can improve the entire network performance by reducing the congestion as well as the traffic flow within the network. The next use is better management. Instead of using the entire network by all the departments of the organization, we can divide the entire network to multiple subnetworks, so that we can assign one or more subnets to each of the department. So in future, if we have any scaling requirements, we can easily add or remove particular subnets from a particular department in the organization. One more use is efficient use of IP addresses. So if we segregate into multiple departments based on the functionalities, we will know which IP addresses are being used by which department. So we can allocate only the required IP addresses to each of the departments. So this will avoid the over allocation as well as under allocation of IP addresses to each of the departments within the organization. We also can have the better security posture within the organization. Let's take AWS Cloud. So here we have a VPC. For example, a project is using this VPC, which has different layers like web layer, application layer, and database layer. So instead of putting all the hosts within a single subnet, we can segregate into multiple subnets like database subnets, application subnets, and web layer subnets. So we can host all the DB servers inside the DB subnet, application hosts in the application subnet, web applications will be hosted in the web subnet. Here we can set up the firewall rules like only the application layer host will access the DB components, and the host in the web layer will access the application components, and external clients will access the host in the web layer. So this way we can avoid the access of DB servers as well as application servers from clients of outside, and also we can avoid the access of DB servers from web layer. So like this, we can arrange or isolate the different functionalities of the project into different subnets, which will enhance security posture of different applications within the organization. These are some of the applications of subnets. We have gone through what is a subnet and corresponding applications. Now let us discuss about Subnet Mask and network prefix. In the previous video, we have gone through the IP address. Please go through the link in the description section to know more about IP address. So when a device is connected to a network, it will get a logical address called IP address. This IP address tells us information about the host part as well as the network part. So there are two types of IP addresses like IPv4 and IPv6. In this video, we will go through IPv4. This IPv4 address consists of 32 bits. IPv4 addresses are represented in 32 bits. For example, this is an IP address. So here it contains 4 octets, each contains 8 bits. So total we have 32 bits. So by seeing this IP address, how do we know to which network this device is connected? So for knowing the network, we need to know what is the network part of this IP address. Out of 32 bits, we'll have network part plus host part. So we can know about the network part as well as host part by using the network prefix or subnet mask. So let us see how subnet mask is used here. Subnet mask contains the bits 1s and 0s. This will mask the network part by corresponding 1s. So for example, this is the IP address. So if we represent in binary, here let us try to convert to binary first. So here we have each octet in terms of 8 bits. So in binary representation, 2 power 0, 2 power 1, 2 square, 2 cube, 2 power 4, 5, 6, 7. So these values indicates the place value corresponding to a binary digit. So 2 power 0 means 1, 2, 4, 8, 16, 32, 64 and 128. So whatever decimal represented in IP address is a combination of these values. For example, if we take 10, that is a combination of 8 plus 2. So this is 1, remaining all zeros. This is corresponding to 10. 0, 0, 0, 0, 1, 0, 1, 0, dot. So next 0 means all zeros. 8 zeros here and then dot. So we have 3 will be obtained by adding 2 and 1. So this should be 1, this should be 1, remaining all zeros. So this should be 0, 0, 0, 0, 0, 0, 0, 1, 1. Similarly, 15 is obtained by adding 8, 4, 2 and 1. So 1, 1, 1, 1, remaining all zeros. So 0, 0, 0, 0, 1, 1, 1, 1. So this way we will represent in terms of binary digits. So now we need to identify the network part of this IP address. Subnet mask will identify the network part. To get the network part of this address, we need to mask corresponding bits with 1s. For example, if we want to have these 8 bits to represent network part, we need to use subnet mask as 8 ones here. The remaining we can put all zeros. So total 24 zeros here. Only the first 8 bits will represent ones. If we perform logical AND operation between entire IP address as well as the subnet mask, we will get the network part. In the logical AND operation, if you have both zeros, the output should be 0. The output will be 1 if both are 1s, otherwise it is 0. That means for 0, 1 it is 0, 1, 0, 0, 1, 1, 1. If we perform logical AND operation here, 0 and 1 means 0. Same way 0, 0, 0. Whenever 1 comes in the IP address, we will get 1. Otherwise it is 0. So remaining part of subnet mask is 0. That means entire AND operation will get 0. So that means this is 10.0.0.0 because all these are zeros. So this is the network part. So if you want to get a network part from an IP address, we need to perform a logical AND operation between the IP address as well as corresponding subnet mask. So here subnet mask will mask the IP address with corresponding ones. Let us go through some of the examples now. In the first example, we need to find the network part and host part in IP address 192.168.1.13 when the subnet mask is 255.255.255.0. So first of all, we need to represent this IP address in binary format. So since each octet represents 8 bits, I have written the place values here from 1 to 128. Each number will be a combination of these values as mentioned earlier. So let us take 192. 192 will be obtained by adding 128 and 64. For all the remaining, we can put zeros. Next 168 will be obtained by adding 128, 32 and 8. Let me put zeros for the remaining. Similarly, 1 will be obtained by putting all zeros except for 1. And 13 will be obtained by adding 8, 4 and 1. So for the remaining, let me put zeros. So similarly, 255 means all ones. So this is 1. So next also 255 and 0, 0, 0. So this is for 0. So this is subnet mask and we have the IP address. We need to put all these things here. So to get the network part, we need to perform logical AND. So if both are ones, then it will result in 1, otherwise it's a 0. So here both are 1s, so that is 1. Similarly, the next one is 1. Since these are all 0, if one of these bits are 0, that means all are 0. Similarly here, both are 1, so 1. So next is 0, both are 1s, 1, 0, 1, 0, 0, 0. Similarly, since we have 7 zeros here, so let us put zeros here, and if both are 1s, it will be 1. So here all are zeros, so it would be zeros. This is nothing but the same value here, that is 192. And next one is, this is the same value, which is 168. And this is also same, like which is 1, and this is 0. So this is the network part. That means whenever we perform logical AND with 255, the same address will be obtained. So here we have 255 for 3 octets. So that means the network part will be 192, 168 and 1. Since here 3 octets represent the network part, the remaining will be host part. So this 13 will identify corresponding device in this network. So let us see another example here. So this is the IP address. We need to find network part as well as host part in this IP address when the subnet mask is 255.255.0.0. So here we have 255 for the 2 octets. That means if we perform logical AND operations, we'll get the same value for these 2 octets. And for the remaining octets, we'll get 0. So that means here the network part will be, so this 50.0 indicates corresponding host part within this network. So this way, if we know the subnet mask and if we know the IP address, we can find what is the network part and corresponding host part. So now we have seen subnet mask. We can also know the network part from an IP address by using network prefix. For example, if we mention like this, here 24 indicates the network prefix. So this number mentions how many bits are used to represent the network part in an IP address. For example, in this case, 24 bits, that means 3 octets will be used to represent network part and the remaining is host part. So this means 192.168.10.25. So this is an IP address is part of network 192.168.10.0/24. So here the network will be represented like this. So this is the IP address for this network and we'll say 192.168.10.25 is part of this network. Here the subnet mask is, so for 3 octets we need to mention like 255.255.255.0. For example, if we say 16, 2 octets will represent corresponding network part. In that case, subnet mask will be 255.255.0.0. So if it is 16, we can say this entire IP address belong to 192.168.0.0/16. So we can say this IP address belong to this network. So this way network prefix can also be used to represent the network part in an IP address. Actually this looks easy when compared to subnet mask, because we can directly specify the number here so that we can know what is the corresponding network address, as well as we'll know the IP address is part of which network address. So by using this subnet mask and network prefix, we can also know the IP address range. So for example, so if we mention the network address something like this, so that means first 24 bits will belong to the network, the remaining part will represent the host addresses. So we'll have a maximum of 2 power 8 hosts in that network. So that will be from 0 to 2 power 8 minus 1. That means 0 to 255. Out of this 0 to 255, 0 represents the network address and 255 represent the broadcast address. So we can use from 1 to 254. So these are the usable addresses within this network. Similarly, if we have 172.16.0.0/16. So for this network, what is the IP address range? So here 16 means the first 2 octets will represent the network part. So remaining 16 bits will be for host addresses. So we'll have total 2 power 16 host addresses we can have. So that means from 0 to 2 power 16 minus 1. So the network address will be 172.16.0.0. So this is the first address, which is the network address, and the maximum address is 172.16.255.255. So this is the broadcast address. So the first usable address will be 172.16.0.1. So the maximum usable address is 172.16.255.254. So this way we can obtain the IP address range by using corresponding network prefix or corresponding subnet mask. So now we have discussed about subnet mask and network prefix. Now let us discuss about classful IP addressing and CIDR. In early 1990s, fixed IP address ranges were allocated to organizations. That means the subnet mask or default subnet mask is fixed. For example, it is fixed like 255.0.0.0. That means only 8 bits are used for network part, remaining 24 bits are used for host IP addresses. Similarly, only 16 IP addresses are used for network part and remaining 16 for host IP addresses. Similarly, 24 bits are allocated to network part and only 8 bits are allocated for host IP addresses. So this way, the subnet mask was fixed in early 1990s. So if we allocate only 8 bits for network part, that is called class A address. If you allocate 16 bits for network part and 16 bits for host part, that is called class B. If you allocate 24 bits for network part and only 8 bits for host address, then that is called class C. Remaining class D and class E are there. Those are reserved for multicast as well as experimental. So this is called classful IP addressing. So in this classful addressing, we have fixed number of bits allocated for network as well as corresponding host IP addresses. So in class A, since we have 24 bits allocated for host IP addresses, we'll have like total 2 power 24. That means these many number of IP addresses are allocated for hosts in the network. Similarly in class B, so we have 16 bits for host. So 2 power 16 total number of IP addresses we can use for the host IP addresses. Similarly for class C, only 8 bits are allocated, so we have total 2 power 8. So out of 2 power 8, so we can say minus 2. So one address is used for network address and another for broadcast address. Similarly here 2 power 16 minus 2, same way 2 power 24 minus 2. So this way the classful addressing was based on the fixed number of IP addresses for each of the classes. So this classful IP addressing is very simple because we only have very few number of classes. That means we allocate only fixed number of IP addresses. The main drawback of this IP addressing is it allocates only fixed number of IP addresses. That means either it allocates very large number of IP addresses or very small number of IP addresses. So if you need in between, for example, in between of these two classes, there would be a lot of waste of IP addresses. Similarly here also, if you need the IP addresses in between, so these number of addresses need to be allocated and will waste lot of IP address allocation. So that is the reason a new method of allocating IP addresses has come into picture, which is called CIDR, which is also known as classless interdomain routing. So in CIDR, in addition to 8, 16, we can also change the network prefix based on our requirement. For example, we can use /14, /20, /22 like this. That means we can assign multiple ranges of IP addresses by using CIDR. I would discuss more about the CIDR when we discuss about subnetting. So let us start with subnetting now. So now let us discuss about subnetting. Subnetting is dividing a larger network into multiple smaller and manageable subnets. So we will divide a larger network to multiple smaller subnets. So for performing this, we'll represent the IP address ranges in CIDR format. Let's take an example 192.168.10.0/24. So here we have 24 as the network prefix. That means the first 3 octets will represent the network part and the last octet will represent the host part. So these are 24 bits and this last octet will represent 8 bits. So for example, if we want to divide this network to 4 subnets, if we want to perform subnetting, we need to extend these network bits to corresponding host part as well. That means we need to extend the network part of this CIDR to some length based on the requirement. So here we have 8 bits corresponding to host addresses. So now we need to extend this 24 to extra bits in the host part as well, so that we can represent these subnets in terms of those extra bits. So how many bits required for these subnets? So here we need to calculate how many number of bits required to represent 4 subnets. So that means we have 2 power x is equal to 4. That means x is equal to 2. So the minimum number of bits required to represent 4 subnets is 2 bits. For example, if we want to make 6 subnets, then 2 power x is equal to 6. So in this case, x should be a minimum value of 3. If x is equal to 3, we can make 8 subnets. Since 6 is less than 8, so this x is equal to 3 would be sufficient. Similarly, if we want to make 10 subnets, so in that case 2 power x is greater than or equal to 10. That means x should be minimum of. So this way we can calculate how many extra bits are needed to represent corresponding subnets. So what are the possible values? 0, 0, 0, 1, 1, 0 and 1, 1. So these are the 4 values we can use for these subnets in addition to these 24 bits for the network. So that means the possible subnetworks are 192, 168 and 10. So this part is not changed. So let us fill 0 zeros for the network addresses. So this is 0. So since we extend by 2 bits, we need to add 2 here, so that means 26. Similarly, the next subnet is 192.168.10. So this value is 64/26. The next value is 192.168.10. So this value is 128/26. The next subnet is 192.168.10. So this is 128 and this is 64. If we add both, this is 192/26. So these are the subnetworks that will be obtained when we divide this network to 4 subnets. Now we have got the subnets. Let us calculate the address ranges for each of these subnets. Let us take the first address. So 26 bits are allocated for network. We'll have remaining 6. That means 2 power 6, 64 addresses. So total we can have 64 addresses in this subnet. So that means it starts 0 to 63. So this is the last address in this subnet. So this 0 means this is for network address and this 63 means broadcast address. So that means we can use the addresses 1, 2. So these are the usable addresses in this subnet. Similarly, here also we can calculate. So this 64 is for subnet address and this 127 is for broadcast. Similarly, if we perform the same for this subnet by keeping this network address constant, so this will range from 128 to 191. So 128 indicates subnet address and 191 indicates broadcast. Remaining IP addresses we can use in that subnet. Same way this will start 192 to 255. So this is for network and this is for broadcast. Remaining addresses we can use. So this way we can calculate the IP address ranges also. Let us go through one more example so that we can get some confidence in this. This is another example problem. The problem is allocate the IP addresses for 4 subnets, which are 2 public and 2 private subnets, each having 256 IP addresses with network prefix /24 in a AWS VPC with CIDR 10.0.0.0.16. So this is the CIDR given. We need to get 4 subnets out of it. Each will have the network prefix as /24. So out of 4 subnets, we can assign 2 as public and 2 as private. We also need to calculate the IP address range of each of the subnets. A note is given. AWS reserves 5 IPs for each of the subnets. That means in each subnet, we have like 5 reserved IP addresses, like first 4 and last one. The remaining IP addresses we can use in each subnet. So let me put here the CIDR. So in the CIDR, the network prefix is given as 16. That means first 16 bits are assigned to network part and the remaining 16 bits are for host part. If you want to have subnets from the CIDR, we need to extend the subnet mask towards host part. So how many bits need to be extended, that we need to find. So here we need to get 4 subnets, each having 24 subnet mask. So this 24 means we need to get each subnet length as 24 bits. That means we need to extend the network part from 16 bits to 24. So we need to use extra 8 bits in the host part for subnets and remaining 8 bits we'll use for host part. So with 8 bits we can have 2 power 8, which is nothing but 256 subnets we can have. So out of these 256 we need to get 4 subnets. This is the requirement. So this is already fixed for network and this is for subnets and this is for host part. So for subnets we can put like this, total 8 bits. So 0, 0, 0, 1, 1, 0, 1, 1, 1, 0, 0 up to all ones. This is 0, this is 1, this is 2, this is 3, 4, 5 up to 255. So these are the total 256 subnets we can get by using extra 8 bits. So out of these 256 we can take any of the 4 subnets. So for this demo, let us use the first 4 subnets in order. That means we can take this one, this one, this one and this one. Once we finalize this octet, so remaining we can assign zeros for the corresponding network addresses. So each address will be 10.0.0. So first one is 0, that's why I'm assigning 0 here. Then 0/24. So we extended 8 bits, so /24 here. So the next one will be 10.0. So this is 1, 1.0/24, 10.0.2.0/24, similarly 10./24. So these are the first 4 subnets I have taken, but we can take any 4 of these available 256 subnets. So out of these 4 subnets, we can allocate the first 2 subnets for public subnets and the next 2 subnets for private subnets as per the requirement. So once we get the subnet CIDRs, it's easy to identify the address ranges. So here 24 means this is 8. We have 8 bits for host addresses. So this will have 2 power 8 host addresses. This is 2 power 8. Similarly, this is 2 power 8 and this is 2 power 8. So for IP address ranges, for example, for 10.0.0.0/24, so it should start with 0 here, then up to 255. So the range will be 10.0.00 to 10.0.0.255. So this is the IP address range for this subnet. Out of this IP address range, it has mentioned that AWS reserves 5 IP addresses, means first 4 and last 1 are reserved. So that means 0, 1, 2, 3 are reserved. And also 255 is reserved. So that means the usable IP address range is 10.0.0.4 to. So this is the usable IP address range for this subnet. Similarly, the IP address range for this is 10.0.1.4 to 254. Similarly for this 254. Similarly for this also from 3.4 to 3.254. So this is the IP address range of each of the subnets. So this way we can calculate the IP address ranges of each of the subnets. So when we perform the subnetting, first of all we need to see what is the CIDR of the input. Based on this we need to identify what is the network part and what is the host part. Then we need to understand the requirement of each of the subnet size. For example 24 here. Then we need to identify how many subnets are required. So finally we need to calculate corresponding IP address ranges. So here we have taken an example of AWS VPC. Similar concepts will be applied for Google or any other cloud. So in this video we have seen what is a subnet and what are the uses, and we have explained the concepts of subnet mask and network prefix. We also have gone through classful IP addressing and CIDR. Finally, we have seen what is subnetting and how it is done. We also have gone through some of the important examples to explain subnetting. I hope this video helps. If you like the content, please like, share and subscribe. Thanks a lot for watching.